with the introduction to the Nernst equation, and we also discussed how we could predict whether the E cell of a particular cell, when the conditions are not standard, whether it's going to be greater than normal, or rather greater than the standard, or it's going to be less than the standard, right? Or rather, when the concentrations are at a standardized form. Now, those were just making predictions whether it will be higher or lower. Now, with the next equation, we now want to figure out what the actual value is going to be, that right. So what we're going to be doing here will be the derivation of the worst of the next equation. So we're just basically going to run through the derivation, and I think that way it's going to be helpful. Okay, so having done that, we can proceed. So then, we know from thermochemistry that the change in free energy is going to be that, and then you are going to have yeah. So we know from studies on free energy. Okay, let me just allow the person to enter. So we know from free energy studies that we are going. Oh, sorry, not from free, from thermochemistry. That okay. So what this equation is telling us is with so that Q there, that in Q, so we see the Q is the reaction quotient, right? So what then we are going to do is, we have now, remember this G that I'm underlining there, the one that is, that's the change in free energy, and you see that it doesn't have that superscript, right? So because it doesn't have that superscript, what does that entail? That entails that it's not under standard conditions, right? So then you want to find what will be the free energy of this particular cell when it's not in standard conditions. So how can we do this? And we can now use this particular equation to actually derive an equation where we can actually find what the cell potential of that particular cell is when the cell is not in standard conditions. And we know what standard conditions are. Standard conditions entails that your concentration for any solutions is what is 1 molarity, right? So things like that, right? And then for a gas, of course, it should be 1 atmosphere for the pressure. So now let's see how we can break this down now to have our next equation that we can be able to use to find the cell potential of a cell when it's not in standard conditions. So what do we know? First of all, we know that the change in free energy, so this one that's not uh, standardized. Okay. So we see this one that's not standardized. It's like that. You see that E, the cell potential doesn't have that superscript because it's not standard, right? Then for the standard, so change of free energy standard, you see that it's pretty much the same thing, but then you see that the cell potential for this one is going to be standard, isn't it? So now, since this is the case, what then we do then is we just try to substitute, right? So we're just going to substitute these things in the equation. So substituting these things in the equation, we are going to have on the left, okay. Then what then we are going to do is, we are then going to divide uh, everything by what? By what's this? By NF, okay? So that's basically saying by the number of moles times Faraday constant. So number of moles, Faraday constant, number of moles, and Faraday's constant. So then what we are then going to have is, so then what we are going to have in this particular case, we are then going to have, so that cancels, you've got the E, and you see that's not standard. The cell potential there, that's not standard. Then we cancel that, you're going to have the standard cell potential. Then you're going to have, because of that negative there, so instead of plus, we are going to have negative there, right? Then we are going to have RT over number of moles times Faraday constant, and then ln uh, of the reaction quotient. So you see that what we have there is what is an important equation. But then what then we want to do? Yeah, so that's an important equation which we call the Nernst equation. Okay, so this is the Nernst equation. Because what this allows you is you can be able to determine what the cell potential is for for a galvanic cell that is not in standard that's not in standard conditions. Okay, so that's why it's very important. Okay, okay. Let me do that. Yeah. Okay. Okay, welcome. Yeah, so that's now there is, so this is a general Nernst equation, right? But there is a way in which you can simplify it, because most of the times the experiments that we do, they are done at room temperature, isn't it? And we know that room temperature is going to be something like 25 degrees Celsius, right? So the so there is so there's going to be an equation that's going to be this same equation, but where there is T, when we substitute the temperature there, 15 degrees, but we know that temperature is read in kelvins. So when you substitute that temperature for what? For room temperature, isn't it? Please, in case you're not asking a question, can you mute your microphone? Okay, yeah. So there you've got the room temperature, right? So now, since most reactions are going to be done under room temperature, so what this entails is that when you plug in that temperature there, and you know that that R, that's a constant that we'll look at when we start dealing with thermochemistry. But for now, yeah, it's not very critical. So now when we do all the substitution, we plug in that temperature there, what we are going to have, and remember, this is only valid, the equation that I'm writing is only valid when they tell you that the equation was occurring at 25 degrees Celsius, right? Which is going to be most likely or almost always, which is going to be a what? Your room temperature. So what you're going to get is, yeah. So what then you're going to get is yeah. So maybe it may not be room temperature, but let's just get it as what? As 25 degrees, right? So let's just get as 25 degrees. So at 25 degrees there you've got that that over number of moles. Then it's no longer lean, it's log reaction quotient. So you see, what this equation is saying is that if you want to find the cell potential with variations from the standard, what you do is that you actually get the. So you see that one that has got like a superscript. Huh? So this one with a superscript, that's for the standard cell potential. Then the n here is for the number of moles. Okay, so this one is for the cell potential under standard conditions. Under standard what? Under standard conditions. Then the n, as we've seen, that's the number of what? Number of electrons which are being transferred. Okay, then for the q, we know that's the reaction quotient, right? Don't worry, we'll discuss how to calculate everything. So that's the equation. Then of course the E without the superscript, that's basically the cell potential not under standard conditions. So not under what? Not under standard conditions. So that's something that's very, very important to take note of. Then having done that, so that's that, right? So that's how we can basically derive that. So now let's see how we can look at an example. But is everyone clear on this one? Okay, so the one that taking the screenshots, you've already taken one? Okay, great. So then, what then we are going to look at then is, let's now look at an example. So an example that we are going to look at is, if we've got this equation, we've got, please, in case you're not asking a question, unmute the microphone. Oh, sorry, mute the microphone. But if you ask me a question, you can go ahead. Okay. So, okay. So there you have, right? So for this equation, so the standard cell potential is what? Is 0.48 volts. Okay? And then you've been told to find what the cell potential of this particular reaction is going to be, and if it's being done at a temperature of, let's say where it's being done from, the temperature is 25 degrees, right? So that's the temperature there. So we know that in this case we have to use that modified equation, which is simpler, isn't it? So what then we are going to do is, we are going to say, okay, so you are going, so having done that, then one thing that you also have to look at is, they'll give you the concentrations, right? So now let's say the concentration. So usually the concentrations you are using to find your reaction quotient. Anyway, let's look at it step by step. So you look at the temperature, then you realize that we are going to use the what? The modified equation. Okay, and you have to know these equations. So that's that. Then the log, then the reaction quotient. So then, yeah, so that's about it, right? So then from here, then what then you do is, you then say, you want then now to find what is your reaction quotient, and they would have given you the concentrations. So the concentration for the manga, for this manganese ion, I guess, so it's going to be 0.5 molarity. So we see that that's not standard, right? They've decreased. And you see that from these, we can even really tell which direction our answer is going to go to. And it becomes very important for you to be able to check yourself if your answer is correct. Because remember, like what we were discussing yesterday, you can be able to determine or at least predict where your reaction is going to go to. So then let's predict, what is our E cell going to be larger or smaller than the standard there? So you see that what has happened. We know that the standard concentration is what? Is one molarity, isn't it? So meaning the fact that you see the product here, the product, remember this is the product, right? That here, the product is more than one molarity. So what that basically tells you is that the product is in high amount. So if the product is in high amount, the reaction wants to go backwards to try to make what? To try to make more reactants so that it can decrease the product. Because remember, the aim is trying to reach a what? An equilibrium in the two concentrations, right? So there we know that our value that we are going to have is going to be less than our what? Less than our standard. Okay? So that's really the context. And then we can even look at it from the reactant side, where you see the reactant is a small amount. So meaning if the reaction goes forward, the reactant will become more. So it will go a little bit backwards, right? So all those things by Le Chatelier's principle tells us that the cell potential that's not standard is going to be lower than our standard. So that is very helpful because it's going to guide you to check your answers to know whether they are correct. Okay, okay. So we know that. Okay, thank you for that. So we know that standard cell potentials, these are calculated when the ions, okay? These are calculated when all the things which are in aqueous solution, they've got a concentration of what? Of 1 molarity, isn't it? So we see that because these, you see that these ones which we've been given, they've deviated from the what? From 1 molarity. So meaning this reaction is, or this reaction is not occurring in standard under standard conditions, right? So now, like we discussed yesterday when we were talking about the Le Chatelier's principle, where we said we could predict what's going to happen to our cell potential based on the equilibrium, right? Because the galvanic cell always want to reach equilibrium. So what's going to happen is you look at any of the two. So let's look at the manganese, for instance. That's a reactant, and we see that its concentration is low. Now we know that under standard conditions it's going to have a molarity of what? Of 1, but there it's got 0.5. So if it's 0.5, that means that the concentration of the manganese ion there, you see that it's what? It's less than the standard. So meaning the reaction wants to go backwards to try to make what? To try to make more manganese what? Manganese ion, so that the concentration can what? Can rise up. Because remember, the aim is to reach equilibrium. You get my point, right? Then so it's meaning that the fact that the reaction want to be going backwards, meaning that the cell potential, the electrons are not going to be flowing the way they want to be flowing, because Le Chatelier's principle is telling us that the reaction will be going backwards to some degree. Then we can also conversely look at the product as well. What are we having for the product? So you see that the concentration of the product has actually been increased, okay, from 1, which is the 1 molarity, which is the standard, to 1.5 molarity. So what does that tell us? That tells us that, this is higher than normal, so or higher than standard. So the reaction want to go backwards. Why does it want to go backwards? So that this product can be retained to this initial that it had. And when that happens, it's going backwards, so as to decrease this concentration to try to bring it to the 1 molarity. And by so doing, because it's now going backwards, the cell potential that we expect to find is going to be lower than the standard. You've gotten it? The one that asked. Okay, great. Okay, great. So now we know our standard is that one there on top, but let me just rewrite it again. Or let me just rewrite it rather. So there we have our standard, right? Then now you want to ask yourself, what is your reaction quotient? So your reaction quotient, you are basically looking at things which are in aqueous solution. So meaning when we are writing this, it's going to be product over reactants, but you're only going to write things which are in aqueous solution. So let's say for the product, we know that we've got the aluminium ion and we've got the manganate there, which is in solid, right? So which one are we going to write? We only write for the product, we only write that one, which is what? Which is in aqueous solution. Then we now go, that's why you have to ensure that your equation is balanced. Then you've seen this coefficient, the 2, in front of this, in front of the aluminium ion, that's what you put there on top. Okay, so Let me rewrite it. So remember I said you only write things which are in aqueous solution. Then you put something on top there, or we can put n, where n is basically the coefficient that is in front of what, of that substance. So you see, for the aluminium it's a 2. Okay, so you've gotten a 2 there. Then yeah, so there's a 2 there. Then now, so we don't write this one because we don't write the manganese on the product side because it's a solid, it's not in aqueous solution, right? So we don't want to write things which are in solution, and we know and we can find the concentrations, huh? So, and we know yeah. So you see now, for the reactant, so we are done with the products, huh? Because we only had one which was in aqueous solution. Then now we now go to the reactant and say which of the two reactants, or aluminium, we see that aluminium on the reactant side is a solid, okay? It's not in aqueous solution, so we don't put it in our reaction quotient. Then we now go to manganese ion. Manganese ion is in aqueous solution, so what do? You write it there. Then what are we going to put there as our superscript? You see, you look at what is the coefficient here. The coefficient is what? Is 3. So here you're going to you put like a 3 down there. Then once you've reached here, really, the tough part is done. You just simply plug in the concentrations. So concentrations for aluminium, we found it's 1.5, 1.50 molarity. Then we put the 2 there. Uh, then for the manganese ion, we put there 0.5. Then it's a 3 for this one, right? So meaning the value of your reaction quotient is what? Is 18. And it makes sense that this doesn't have units, because remember, you are squaring you are square here, you have got molarity squared, and these are cancelling, right? So that's how you can picture. That's why it doesn't have uh, units, huh? The reaction quotient. So having done that, so we now have our reaction quotient. What else do we need? We now have to calculate our n. We have to find how many electrons were transferred, because remember that for our equation, for us to use this equation again, we are using the simplified one, because we know that the reaction is occurring at a temperature of what? Of 25 degrees. So we are using this equation. So we found our reaction quotient, which is the Q there. Now we want to find the N, okay? Because we already know what the standard cell potential is. Yeah, but sometimes you may be required to calculate it, right? But we already know how to calculate. So anyway, so now we want to now find out what our n, the number of electrons which were transferred. And for this you can't do it without what? Writing the reduction half reaction and the oxidation half reaction. So when you ask yourself there what's happening to the aluminium, it's the oxidation state is what? Is increasing. So meaning that it's what? It's being oxidized. So meaning you say aluminium, if you are so anyway, let's not put state symbol, but you could put state symbols if you wanted. Anyway, there's no harm, let's do it. So it's been oxidized. There's a cap 3 there. So if it's plus 3, to maintain, to balance the charges, it's going to be how many electrons? 3, huh? But don't write 3 electrons yet. Remember, we have to balance the equation, huh? Then for this one, we are having, for the manganese, we see that it's so let's write it like this. So for the manganese, we see that it's M N. Then that's it's the one that's being reduced, right? So it's an ion. So this is what's being reduced, and we see that's 2 plus. So meaning 2 electrons, right, are being added to form the manganese solid. So meaning the one that we have here on top is the what? Is the oxidation half reaction. So that's the oxidation half reaction. Then the one that we have down is the reduction half reaction. reduction half reaction. So there now you want to balance. How do you balance the electrons to be 6? So you say, okay, I can make the top one 6 if I multiply by. So you look at for the lowest common multiple. Lowest common multiple of what? Of 2 and 3. Yes? Okay, so that equation that you are looking at is an already balanced equation. Okay, so but for you to find the number of electrons which were transferred or transferred from the anode to the cathode, you have to practically do the balancing, because that's when you're going to find the number of electrons that were transferred. Okay, which which equation? Which one? Which first? This one, the one that I've ticked. Yeah, so that's what I'm saying. That's the full equation. But for you to find the number of electrons which have been transferred, you have to balance the equation. Okay, just wait. You see what I'm talking about. Just give me a minute. When I'm done explaining, I'll ask you if you've understood. Then you let me know, cause yeah, just let me finish. You get the point when I'm done. So you are trying to you're trying to rebalance, to check the, or rather to do as though you're trying to balance the equation so that you can find the number of electrons which have actually what which have actually been transferred. So you look at the coefficients between before the numbers before the electrons. It's what is 2 and 3. So you ask yourself, what's the lowest common multiple of 2 and 3? It's 6, right? So 6 is the number where both 2 and 3 can go into. Okay, or you can say multiple, or if you want you can say a number in which both of them can go into. So meaning, how can I make the top equation to have this electron to be 6? I'm going to multiply the entire equation by 2. Then how can I make these 2 electrons to become 6? I'll multiply everything by 3. So then what then you are going to do is, so what then you are going to do is, so the top equation becomes that, then the other one becomes, so that's how they balanced that equation there. But we can't just simply use that. Okay, if you want, you could use that equation, and I'll show you how you could use it. But I would want you people to be comfortable with being able to do these things, because that way you can be able to, because usually they may not give you a balanced equation. So you may want to know this. So you cancel the electrons. Then when you write it, you're basically getting the same equation that we have there on top. So that's how they balance. But of course, we know that what we were really interested in was what was finding the number of electrons. So this route that I've taken is the long one, and I've done it so that we can appreciate this. But what we wanted was what number of electrons is, what is 6. Now, how can you figure out? Okay, so the one that was asking you, you've now gotten the point of us going through this route. Okay, great. So now, from this reaction, we can directly, you can figure out how many electrons were transferred. So you just focus on one thing. So since it's already balanced, just look at two two moles of aluminium and 2 moles of what? 2 moles of aluminium ion. So you say 1 mole of aluminium 1 mole of aluminium to be converted to 1 mole of aluminium ion, it takes how many electrons? 3. So how many electrons is it going to take? 2. So it's going to be there at 2, there at 2. Then you multiply this 2 by 6. Oh, sorry, 2 by 3. So you're going to have 6 electrons. So from there, you can find your N to be 6. But of course, this can be tricky and you may be prone to making mistakes. So that's why I prefer that we used that other approach. So here now we've got our reaction quotient. We've got our reaction. Hello? What are you saying? Oh, you can use, okay, you can use either. Okay, let's use the one for the reduction. So for the reduction, you say, so that's manganese ion. Then for it to become just a solid, meaning how many electrons went into it, meaning how 2 electrons, right? Then you see how this is balanced. Then you say you've got how many moles? 3 moles. So 3 moles, that's you put a 3 here. Then 3 times 2 again, you are going to have what? You are going to have 6. Then here you put a 3 again. So you see either way, you are getting 6 electrons. So you can use either. But of course, most times they will not give you a balanced equation. But sometimes they might. So in case you see that the equation is balanced, you can. But again, sometimes your marking key tends to be very, very tricky. And because Zoomda shows the procedures like this, sometimes they may want you to show them like that. But otherwise, that you could use that short method. So that would be something good to ask your demonstrators or your tutors. But basically, yeah, you could use the short method. But depending on on how your marking key is, you may want to go through the long route so that you don't miss any marks. Since it's pretty short, right? So yeah, but so to answer your question, you can use either the one being reduced or the one being oxidized. So then, we can now write our equation once again, our modified Nernst equation. So for our modified Nernst equation, so you basically just plug in the things that we found. So this one, then we've got that over 6, n is 6, then the reaction quotient was 18. And once you plug in, remember from our prediction, we said it should be what? It should be less. So again, here to avoid making errors, I would encourage that you just drop this, because again, many people here, it can be easy to make errors. So you okay, let's just remove that sign. That okay. So yeah, so you may want to do it separately, where you do this calculation separately. Okay, so by doing separately, yeah, I'm saying this because sometimes it's very common for people to make mistakes. So you do that calculation separately, you do this calculation separately, and that way you reduce the chances of making errors. So you've got 0.48. So you see that we are basically maintaining this. Then we are having, so when you deal with this, you are simply going to have 0.01. So you see, this is a better method because you are less likely to make mistakes. And like we had predicted, this is less than the standard, isn't it? Because we had predicted that what we would get would be less than the standard value. So basically, that's how you deal with the Nernst equation, and then yeah. So that's basically how you deal with these kinds of questions. Yeah. So that's how we deal with those kinds of questions. So now, should we do another example, the one that's involving more things, or maybe people are comfortable with this example? Or maybe, okay. So before we can talk about how we can find the equilibrium constant, uh, with this, let's look at another thing. So what we are having here is uh, these equations. Yeah. So really with these things, the more you practice, the quicker you get, and yeah. But it's one topic that I can promise you, once you get the concepts right, you can consider these as free marks. So it's just you have to perfect your skill, but these are really free marks. Okay, uh, so we've got this, and then they will give you the cell, the standard, the standard reduction potential for this. So that's 1.00 volts. Huh? Then you now go for the then the other one. The other one they're giving us is zinc. So you see that they're giving us both written in their reduction, right? So they expect us to figure out which direction the equation is going to go to, which are the things we've been looking at in the past lessons. So in case you are not sure how to go about this, you can check the Google Classroom. I've uploaded everything that we did yesterday. So from this, which one is going to be the cathode, which one is going to be the anode? So remember, the cathode is going to be the one which reduction potential is what is greater, right? Or is more positive than the other. So we see that by that token, we know that the first equation, this one, is going to be our cathode. So we know that this one is going to be our cathode, right? Then this one is going to be our anode. So if this one is going to be our anode, already we know that we have to rotate it. So rotating it is going to be this. Okay? So if we do this, you see that the E cell is rotated. It has become like that, right? So that's our anode, that's our cathode. So then what do you want to do then? Then we want to then be able to balance our equation. So that's why even in the previous thing I wanted us to talk about balancing these things, right? So meaning, having done this, so now if we want, we can wrap this part so that we save time. So then you are now asking yourself, okay, let me write it on this side so that we can, I don't have to rewrite everything, so that we can save on time to look at a number of concepts. So then what you have, so you've got your cathode and you've got your anode. And are the electrons, you see here is 2, here it's, oh sorry, pardon me. So you see that here it's 1. So then what you have to do, so meaning you have to multiply, oh sorry, I ended up deleting that. Okay. Yeah, so you see that here it's 1, here it's 2. So what you do, you have to multiply this reaction by what? By 2, right? So that the electrons can be equal, so that they can cancel out. So meaning our cathode reaction, we are going to multiply everything by 2. So we do that. So remember the state symbols, always put them uh, aqueous, aqueous, and then that would be aqueous, then that's water, liquid, because these things are dissolving in water. So then what then you do at this point is, yeah, then you get the anode reaction. So then what then you do is, you want to combine the two equations, right? So what you do is you cancel the electrons, right? So electrons get cancelled. So meaning your equation is going to. Now, why is this process important? Because you can't find your reaction quotient without having a correct equation. So if you get this equation wrong when deriving it, you've gotten everything wrong because your reaction quotient is going to be wrong. Okay? So you do that. Then, oh, sorry, I forgot state symbols here. Yes, they should be there. So there we have zinc solid. Then that's going to be that. Okay, great. So you see, so now we now know how our reaction is going to look. So from here we can calculate our standard cell potential, right? So we say it's the cathode plus the anode. So the E of the anode, oh sorry, yeah, so you're just adding them. So what's our cathode? So our cathode was what? Our cathode was 1.00 voltage, and then the one that we rotated was 0.76. Again, I discussed yesterday the two ways in which you can find this, and since I explained it yesterday, so we don't have to go through it. Okay, so that's that. That's that. So we found that, right? So now what else do we have to find? We have then to find our, so for our n, we know what our n is already. Those were two electrons that were being transferred, isn't it? Here, these two electrons, right? So our n is 2. So now we have to find our reaction quotient. So they'll give you concentrations, right? And so for this reaction, first of all, they tell us that the temperature is it's at 25 degrees Celsius. So we know that we can use that modified Nernst equation. Then they then give us the concentrations and say, so the concentration there is 2 point, yeah, 2.0 molarity. Then you are going to have for the hydrogen ions. So for the hydrogen ions, you are going to have 0.50 molarity. Then you are going to have for the V, okay, for this one, okay, then you are going to have what? It's going to be, oh, this is a small concentration, so it's going to be 1 times 10. Okay, let me write it properly. So it's going to be 1 times 10 to power negative 2 molarity. Then for this one, so you see, you could have questions which are this complex. That's why with practice you become more accurate. Then there you have that. That's negative 1 molarity. So you've been given all this information. So then what do you do? So what then you do is you then want to look at now how do you calculate your reaction quotient. So remember, you only get so you get the reactants over the what over oh, sorry, you get the product over the reactants, and then uh, you look at the coefficients that are on those species that you're going to look at. So, and then you only write things which are in aqueous solution when you are calculating your what, your reaction quotient. So what is what? So we see on the product side we've got that, and then raised to power 2. So we are raising it to power 2 because you see the coefficient there is what, is 2. Then the other product there is what, is zinc, of which zinc has got a coefficient of 1. So there's nothing that we are adding there. Okay. Then so we are done for the product. We don't put the water because water is not in aqueous solution, huh? Or it's not in an aqueous state. Then we now go to the reactants. So reactants, we get this, and then you see that it's in front of it there is a cut 2 there, right? So let me do it like so we can see that 2. So I'm sure you can see that 2 there. So that's why we put a 2 there. And then we go to the other, which is hydrogen ions, and the coefficient there is 4. So that's why we are having 4 there. So with this now, you just have to start plugging in the concentrations and doing the relevant algebra. So what we are going to do is we now put the concentrations. So ideally, other people may want to do all of this uh, within the next equation, but others may want to calculate it just from there, right? So different people have got different preferences. So if you want, you can leave it from there, then you then write the next equation. So we know that it's occurring at 25 degrees Celsius, so we can use this modified. Since this one is the simplified at 25 degrees. So what then you do is we calculated our standard cell potential, which was what 1.76, then 0.051 over the electrons we had 2, right? Then log. Then again, you see, like I said, other people may want to do it within the equation, others want to calculate it separately and then just plug in the value, right? So either way, you're going to get your answer, right? So what you do is, since we've already, anyway, let's just write there so we can be able to appreciate it. So okay, so there you have it, right? So then what you're going to do here, you just start plugging in the what? Just start plugging in the values, which you've already started doing. So you just want to plug in there 1.76, then here it's 0.5912, then log. So the concentrations now, we now start writing the concentration. So we know the concentration for the V2 and everything, that was 1 times 10 to power 2, then you square that. Then for the zinc it's going to be 1 times 10 to power 1. Okay, so we don't raise that to any power because of how the equation is, right? So once we have that, so again we know that all this is under that, then over. So you see, sometimes you may want to write it like this, or you can want to calculate it separately. But either way, you will get your answer. So then for this one, then there. So now our E is going to be 1.76. So then, so So that's about it, right? So these may be a little bit lengthy, but that's how you that's how you get a hold of them, right? So that's that. Are there any questions? Okay. So if there are no questions, then we can proceed to look at the next part. So ion selective electrons. So really, there's nothing much to talk about these, but the ion selective electrodes. These are basically uh, certain instruments which you can use to actually record and calculate specific uh, ions. Okay, so for instance, you have maybe let's say a pH meter. So a pH meter, this is an instrument that you can actually use to calculate the pH of a what? The pH of a solution. So, but how does it work? It's that it's been made, or you can look at the structure there. It's been made to only be uh, capable of what? To only be capable of measuring the what? The hydrogen ions. So that's why they are called the ion selective electrodes. And these are important because this can enable us to calculate the pH of different substances without us having to do much work to do titrate and all those things, right? And so these are very important because there are certain things whereby maybe you want to and there are different kinds, right? So the pH meter is the one that of course pH, we know that pH is as a result of a function of what? Of hydrogen ions. So a pH meter is selective for the what? For the hydrogen ions. But you can have also other kinds of electrodes which are going to be sensitive to to the concentration of a particular ion. And so you can have these instruments that are for sodium ion, for potassium ion, or even ammonium. So these are very, very important in the measurement of these things. And so the table there you see on the far left is just giving us just some ions which are very, very important, and you may want to measure them quickly in certain amounts, such as the amount of fluorine, because you know that too much of fluorine or fluoride can affect your teeth, and so things like that, right? So you can actually find the concentrations of these particular ions using the ion selective electrodes. So that's the chemistry behind them. Now, there is an important, interesting point that we have to look at, and this is the calculation of equilibrium constants for redox reactions. So remember what we had discussed, right? Is the quantitative relationship between the standard cell potential and the change in free energy standard allows calculation of equilibrium constant for redox reaction. So what happens when a cell is at equilibrium? So when a cell is at equilibrium, here's what happens. First of all, the cell potential is going to be zero. And when a cell is at equilibrium, that's what we say at the battery is dead. Okay, it's simply because it's not producing any work. Okay, remember we said work is equals to what? Is equals to minus q uh times what? Times the cell potential, isn't it? So if your cell potential is zero, meaning that your work is going to be what? Is going to be zero. That's when we say that the battery is dead. Okay, and then the other condition, so there is that condition where the cell potential is going to be zero, and then your reaction quotient, okay, your reaction quotient is going to be what? Is going to be equal to the what? To the equilibrium constant. Okay, so once a cell is at equilibrium, you are going to have these things. So what does this entail? So now we can actually apply these concepts. Okay, we've run out of time, but let's just look at this equation and then we'll do examples tomorrow. So you see, so the next equation that we have there, We are just substituting. So we know that when a reaction is at equilibrium, the cell, and look at that E cell. That E cell is not standardized. Okay, it's not a standard cell potential. So that's why we see that the zero we are putting it where on the far left. Okay, where the cell potential is not a standardized one. Then we now have that standard. We just leave it like that, and then where we had the reaction quotient, we see that we've put the K or the equilibrium constant, right, according to the conditions for equilibrium. Then once we have that, we just simply make log K the subject of the formula. So what do we do? What we do is that we basically move. Okay, let's just write this so that we can appreciate it quickly, and we can be able to start the other course. But I just feel that if we do this, it will be helpful so that tomorrow we can just look at examples. So what we're basically looking at is this. So we have this, of course, the fact that we are using this equation. So we are assuming that this reaction is at 25 degrees. Okay. So now what then you have is, remember when it's at equilibrium, the E. Remember this E is this one, right? Because it's not standard. And then your reaction quotient is what is equal to K. Okay, so then what then are you going to do? So basically what you do is you are then going to what, to do your substitution. So you put here where there was E, there you put 0, then you put that, then you put 0, that, that over n, then you substitute where there was the Q, you put the K there. Okay, then what do? You want to make log K the subject of the formula because you want to find the equilibrium constant, right? So what you then do is you can move this thing, move it this side so that it becomes positive. Okay, so it becomes positive. So then that's n log K. Then that's going to be E. Then what you're going to do then here at this point is you can then cross what? You can cross multiply. So when you cross multiply, what's going to happen? Uh, what's going to happen is you're basically going to have the same log K. Let's put brackets there. So log K, that's the equilibrium constant. Then you're now going to have the n. The n that was there has been cross multiplied, right? So you're going to have number of moles on the moles of electrons, that, right? Then what else do you do? Then you want now to divide to get rid of the 0 point that on this side and then on that side. So once you do that, then you've got the equation that you can use. So then you cancel that, then you're going to have log K. So what you then do once you found your log K, you just have to find the log inverse of the K. Then you've gotten your what? You've gotten your equilibrium constant. So tomorrow, this is the equation that we are going to make use of. Yeah, and after that we talk about batteries, we talk about corrosion, then we are done with electrochemistry. So basically that's what we'll be looking at. So maybe probably tomorrow we can be able to wind up to finish the